You probably see titanium every day without even realizing it. It's in your phone, your laptop, maybe even in the screws holding your glasses together. It's light, incredibly strong, and doesn't rust. Surgeons trust it enough to put it inside the human body. Fighter jets depend on it to stay airborne at supersonic speeds. But here's the thing: titanium is the ninth most abundant element on Earth. It's everywhere. So, why is it so expensive? And why is making it so ridiculously difficult? The answer isn't what you'd expect. Let's start with where titanium comes from. It doesn't exist as pure metal sitting in the ground. Instead, it's locked inside minerals, mostly one called rutile, which is a compound of titanium and oxygen. You dig up this sandy, dark mineral from beaches or ancient riverbeds, and what you have is titanium dioxide. It looks like powder. It's actually the same white pigment used in paint, sunscreen, and toothpaste. But turning that powder into the shiny metal we recognize, that's where things get complicated. For most metals, the process is straightforward. You heat up the ore in a furnace, the metal melts, impurities burn off, and you pour out liquid metal. Simple. Titanium refuses to cooperate. When you heat titanium in the presence of oxygen, it doesn't purify. It binds even tighter to the oxygen. Heat it too much, and it'll grab nitrogen and carbon from the air too, turning brittle and useless. Titanium loves to react with almost everything. So, in the early 1900s, scientists had a problem. They knew titanium existed. They knew it had incredible properties, but no one could figure out how to make it. Then, in 1940, a metallurgist named William Kroll developed a process that actually worked. It's still the main way we make titanium today, more than 80 years later, and it's wildly inefficient. Here's how it works. First, you take that titanium dioxide powder and mix it with chlorine gas and coke, basically carbon. You heat this mixture to around 1000 degrees Celsius. The chlorine rips the oxygen away from the titanium and forms titanium tetrachloride, a liquid that looks like water but reacts violently with moisture in the air, creating thick white clouds. Now you've got liquid titanium tetrachloride. Still not metal, still highly reactive. Next comes the Kroll process itself. You take that liquid and drip it into a sealed steel reactor filled with molten magnesium, heated to about 850 degrees Celsius. The magnesium is a stronger binder than titanium. It steals the chlorine away, leaving behind pure titanium and magnesium chloride as a byproduct. But here's the frustrating part: the titanium doesn't come out as a smooth ingot. It forms as a spongy mass full of holes mixed with leftover magnesium chloride. It looks like a giant metallic coral reef. You have to break this sponge apart, crush it, wash away the salts, then melt the titanium sponge in a vacuum furnace to avoid contamination. Only then do you finally get a solid block of usable titanium metal. The whole process takes days. It's done in batches, not continuously. It requires extreme temperatures, toxic chemicals, and sealed environments. Every step has to be carefully controlled because titanium is so eager to react with anything around it. This is why titanium is expensive. Not because it's rare, it's abundant, but because extracting it is incredibly energy intensive, slow, and requires expensive equipment and materials. Compare that to aluminum. Aluminum used to be more valuable than gold in the 1800s. Then inventors figured out how to extract it using electricity in a continuous process. The price collapsed. Suddenly, aluminum was everywhere. Titanium is still waiting for its breakthrough. Scientists have tried for decades to find a better way.